Okay, and yeah, welcome back for Twosome. If you have any questions, comments, concerns, put them in the chat and I'll see them. But let's read through the question and we'll get going. So Twosome says, given an array of integers called nums and an integer target, we want to return the indices I and j such that nums at I plus nums at j is equal to the target number. And also, I cannot equal j, or I should not equal j. We get a little bit of clarification here. We may assume that every input, so every array has exactly, or every array in target has exactly one pair of indices I and j that satisfy the condition. So there will be an answer and there will only be one answer. And we want to return the answer with the smaller index first. Fun fact, actually, this is different from the LeetCode version. I think the LeetCode version has been updated so that you can return the answer in any order. In this case, we're going to return the smallest index first, which is not a huge deal. Okay, so here's a couple examples. The first one gives us this nums array input 3, 4, 5, 6 with a target of 7. And the output is 0, 1, and this is because the element at index 0, right here, the first guy, plus the element at index 1, this guy right here. Those two added together, 3 plus 4 equals 7. And as mentioned in the problem prompt, there's only one pair that works. Yeah, and that's that. And notice also, in terms of this, the specifications for this problem, we're told to return the smallest index first, so we return 0, 1, and not 1, 0. Okay, similar vibe here. 4, 5, 6, the target is 10. Notice here, just to clarify one thing about the problem, we cannot return 1, 1 as the answer here because we're not allowed to use the same index twice, which is totally fine because there is a different and better solution, which is 0, 2, number at index 0 plus number at index 2, 4 plus 6 equals 10. And that's what we're looking for. Okay, on the other hand, this one does work because we actually have duplicate 5s here, so we can add together the element at index 0 with the element at index 1. 5 plus 5 equals 10, and there's your answer. A couple additional constraints they give us. The length of the nums array is going to be between 2 and 1,000. Okay, it's actually not a huge deal to us because we're going to tackle it the same way regardless. And the numbers themselves are between negative 10 million and positive 10 million. Same with the target is between negative 10 million and positive 10 million. You may be wondering, like, why is this important for us to know, or why is this an important constraint? If you have taken 325, CECS 325, or maybe you just know a little bit about programming, you may have heard of this thing called integer overflow. Basically, when numbers get too big to be stored in the way that computers store them, sometimes they do weird things. So in this case, basically what this section assures us of is the integers will not overflow. They will behave in normal number ways that you don't have to worry about. I think, just random tidbit, I think Python has a lot of handling for like exceptionally large and small numbers, like a big int type thing. So with Python, it's even less of a worry because it tends to be handled for us. Okay, let's diagram the problem, go over a naive solution, and then we'll tackle a more elegant solution after that. It doesn't actually matter. I can come up with an array myself. Okay, so let's say we had some arguments that went like this. Let's say we've got an array that's got, maybe we'll keep it simple. Maybe we've got like 2, 7, 5, 1, 4, and I suppose actually as a note here, the numbers that, or the arrays that we saw here were all sorted, right? They all went from smallest to largest, but there's actually no constraint in the problem that tells us that the array has to be sorted. For this reason, it would actually be incorrect for us to just kind of move the ends inward or look from the outside in to find the correct sum unless we sorted first. And that actually is one of the solutions, which we'll talk about shortly. But let's say the array is unsorted. It's got things out of order. What could we do to tackle this? Well, one naive solution would be, as we've been doing for pretty much all the problems so far, would be to start by let's actually start with this one. Start by saying, okay, let's assume that one of the numbers, or let's just try and treat the first number, or we'll treat each of the numbers as the first number of the answer, right? We'll say something like, well, maybe it's the very first number of the array, it's 2. And maybe it gets paired up with this one right here. I'm just realizing I actually forgot to provide a target. Maybe the target is 8. Does anything else ever add up to 8? No, I think, oh no, there's 2, yeah, only one thing adds up to 8. So we'll say our target value is going to be 8. That's an ugly 8. Oh my gosh, I did another ugly 8. Okay, there we go, 8. I did eat, thank you. Okay, so we might take 2 pointers, in this case just index numbers, and basically just check, does this add up to the target? And if so, we'll return that pair of numbers. Now obviously 2 plus 7, I hope you know, does not equal 8. And then we could move this number along and say, okay, clearly these two numbers don't work together. Let's keep the first index the same, but move this one over. 2 plus 5 is 7, that's not correct. 2 plus 1 is 3, not correct. 2 plus 4 is 6. And now we've gotten to the end of the array with that second index without finding 2 numbers that summed up to the target. This means we can say, well, 2 is definitely not part of the answer. Let's slide this over and start considering that maybe 7 is the first number that we should return. Okay, well, we'll have our second pointer, or second index, just right to the side here. 7 plus 5 is 12, that's not our target. Finally, we get here, 7 plus 1 is 8. And now that we've found 2 numbers that add up to the target, we can grab their indices, which we've been keeping track of by sliding them along here. And we would return, in this case, that is barely a bracket. We would return 1 for the first number and 3 for the second number. Okay. Now, in the worst case scenario, and in fact, I'll rearrange the array here to illustrate this. In the worst case scenario, I guess I didn't need to move the 1. Maybe it looks something like this. And we would have to consider every single possibility until at the very last one we got the target. So essentially what we might have to do is we might have to make 5 comparisons, or 4 comparisons to start with. 2 against all the numbers that follow it, and then 4 against all the numbers that follow it, and then 5 against all the numbers that follow it, and then 7 against all the numbers that follow it. So we might have to make every possible comparison here before we get to the answer. That would be what we describe as an O of n squared solution. Why is it n squared when we're chopping off a bunch of comparisons in the front? This is actually kind of a neat visual proof that I was taught at one point for recognizing that this is O of n squared. If we were to kind of make tally marks for each of the comparisons that we make, we start by making 4, and then 3, and then 2, and then 1. And so although this is reduced from truly doing like 5 squared or 4 squared calculations, this is literally half of a square, right? Like the other half would be over here. So in terms of the time complexity, hopefully you guys are aware on some level, we throw away constants and coefficients, right? Or I don't know why I said c squared, 1/2 n squared. So in terms of overall time complexity, this is definitely still n squared. And we can do better than that, it turns out. But let's let me think. Let's code through the naive solution, and then we'll talk about the improvement. So hopefully this format is pretty familiar for you, but if we needed to go through each of the elements in an array, we could do something like for I in range len nums. So this is saying for the first number, consider each of the indexes from 0 to the end. And then for j in range, and then so what we wanted to do for that red pointer was we wanted to say, hey, go ahead and start with the thing after I and go all the way to the end. So we can state this as for j in range, starting at I and ending at the length of nums. We could say something like if nums at I, well, and this is the condition that they stated right here, if nums at I plus nums at j is the target, then we can go ahead and return, and what we want to return is the indices. We know that I is the thing on the left, so we can return I first and then j second. And this will do it. We're guaranteed that there is a solution, so we don't have to do something like a return none or anything like that. That's not needed. And this will do it, unless I messed something up. Great. Okay, so let's talk about how we can optimize this. The thing that is causing our code to run slower than it needs to here is that every time we look at a number, we have to search through the entire rest of the array as we go, right? And as we've been talking about, we have these efficient data structures that use hashing to let us know what we have and haven't seen before. And that's a very quick way for us to do basically the second part of the check, which is like, have we seen a number that would work for us? So here's what we can do is we can, instead of having 2 pointers running around, we can just start with 1, and we can say, hey, if I have seen the number that I need to make the target, then go ahead and just return it, right? So let me actually rearrange this so we don't have to do the whole example. Yeah, I'd like to move this one up here. Okay, so we can start at the front and say, hey, I'm looking at the number 2 right now, which is at index 0. If its partner, if its complement is here, it's going to be 6. And we need, again, some quick way of figuring out, have I seen the number 6 yet? Like we talked about in day 1, one really great data structure we can use for this is a set. Obviously, when we start, there's nothing in that set, so obviously 6 can't be there. But what we can do is we can say, hey, and some of you may be going, I don't think you should use a set, and that's correct. Talk about it in a sec. So what we can do is we can say, hey, I've seen 2 now. Before we get too far into this, the problem with using the set solution is that we are going to have to return the index eventually, right? So just knowing that 2 was there is not sufficient for us because we're not returning the numbers, we're returning the place where that number was. And thankfully, in day 2, so it's kind of perfect that we're talking about this on day 3, in day 2 we talked about a different data structure where we can store the things we've seen and an additional piece of information about the things we've seen. And that data structure was called a hash map, or in Python, a dictionary. So here's what we'll say this dictionary kind of encapsulates, is we can say that this dictionary stores a value we've seen before and the index of that value in the array, right? Okay, so instead of just storing the number 2, we'll say, hey, let's go ahead and store the number 2 and store also its index, which is 0. Okay, and again, the reason we stored it is because we didn't find its complement, which is 8 minus 2, 6. Hopefully that's like pretty easy to do. So then we move on to the next number and we say, hey, what number would have had to be present for it to pair up with 7? Well, 8 minus 7 is 1, so we ask ourselves, have we seen 1 before? Again, we can very quickly search through this, sort of the superpower of the hash map here, and we say, nope, we haven't seen it before, so let's go ahead and store this value and the index it came from, right? Keep going. If the partner of 5 is here, it would be 3. Have we seen 3 before? No, we haven't, so we put 5 in here, as well as its index. And then finally, we get to 1, and we say, hey, its partner would be 7. Have we seen a 7 before? And the answer this time is yes, we have. It was at index 1, and so the thing we would return, well, let me actually just set up the structure here first. The thing we would return is this index right here, and then this index right here as the second element. And we know it's going to be in that order because we're going from left to right, so the thing in the dictionary is going to be the first element, and the current index that we're looking at is going to be the second element. Again, this whole idea of being able to search through elements that we've encountered before is a perfect job for hash data structures, hash sets, hash maps. And we prefer the map here because we have an additional piece of information about the keys that we want to kind of pair up. It would totally, actually, one way we could do this with a hash set, if we wanted to, is we could store, you guys are going to give me shit about this again. We could store tuples. So instead of doing a dictionary, we could say, hey, let's actually go ahead and just make a hash set. And in this hash set, not only, well, actually, you know what? Could we do this with hash set? We kind of couldn't, because the tuples, we would have to know ahead of time. So actually ignore what I just said. No set solution here, because we would need to know the index ahead of time to search for something in that set. So pretend I didn't say that. Okay, and that actually pretty much is the solution here. I think someone just hopped in, so welcome. If you're wondering what we're looking at, we're about to go back to the NeetCode page, but this is TwoSum. Any questions, comments, concerns? Great. Hopefully this is pretty straightforward. Great, so yeah, again, just to sum up the strategy before we go and encode it here, we're going to have a number-based or range-based pointer. Hell yeah. That goes 1 by 1 through each of these. If we find, if we find its complement, the thing we would need to add in to make the target, in this hash map over here, then we can collect that information and return it. If we don't, then we go ahead and put the thing we found, like this, in the hash map, and we also store its index so that we have it for later. And again, the reason the hash map's useful to us is because we can search through the keys very efficiently. Okay, so the whole like searching for a value we've seen before, hashing, something we love. Okay, let's code up the solution. We're also, I have an extra little tidbit that you can use here. Hello, I want to click the console button. It's not well spaced. Okay, so let's take a look. We can keep this part, but I actually want to share something that you can do here to kind of clean up your code a little bit. Remember earlier, in order to access these elements, we were saying like nums index I, right? One thing we can do to kind of clean that up and also just be a little bit more descriptive is we can say this, we can say for index and value in, and I'm going to say enumerate nums. And what this does for a list in Python is it says, hey, go ahead and pack 2 pieces of information into each of these loops. One of them is what's the index that we're currently looking at, and then what is the value at that place. And so this just lets us be a little bit more descriptive and a little bit less like programmy syntaxy. And we can do something like this. We can say, oh, well, first we need a dictionary actually. Maybe we'll say like, well, we can literally call it value to index. Okay, so this is going to be our dictionary. And we can say value to index. Oh, actually, no, we don't want to say it yet. We can say if, value, which remember is the key, right? So if the value is in the keys for the dictionary, oh, no, that's not what I'm looking for, because what we're looking for is actually the complement, right? Like if we're looking at 2, the thing we want to find is 6, right? So I was incorrect here. Let's say complement equals target minus value. Okay, so if we find the complement in that dictionary, then we can go ahead and return the index that went with it and the current index. Again, we put this one first solely because we know we encountered it first. So it has to be the smaller of the 2 numbers and then the current index that we're looking at. Okay, so if we find the complement, we're good. We're set to go. We found it. We know what index the complement is at. We know what index we're currently looking at. We're set to go. And from here, we can say, and we'll tidy this up in a second, if we don't find it, then what we need to do is record that we've seen this number before, right? So value to index for value equals index. Okay. And again, at some point we're guaranteed that there will be an answer, so we will hit this. We don't need to write like the rest of the statement. And in fact, because if we hit this condition right here, we return immediately, we don't even need to write this else. We can actually just say, hey, assuming we even got here and we didn't return, go ahead and store this in the dictionary, right? And that's it, I think. Does this syntax make sense? Any questions about like the enumerate syntax? Yeah, so enumerate actually does different things to different data structures. For a list, which is what we got for nums here, what it does is it, instead of forcing us to only use the index or the value, it actually gives us both of those pieces of information, and we can store them in variables like this. So, for an array that's got these indexes, and maybe the numbers are like like that. Each of these loops is going to give us the index and the value at the same time. And it lets us name them, right? So we can say, yeah, very coincidental numbers, right? We can say index and value, but these are arbitrary names. We could say I and V, and it lets us refer to them in these inner loops, right? Instead of forcing us to use just the index number. That's you. Instead of just forcing us to use the index number, or just forcing us to use the value, like a for each loop, we get to use both at the same time. So if both of them are valuable to us, instead of constantly having to like, here's the index and then let me refer to the thing at that index, we can just give them names right here, which is nice for making your code a little bit more expressive and a little bit more readable. Does that clarify enumerate? I hope you do see. I'm also just realizing I'm attempting tonight just to record my the screen that I'm sharing, so I'm gonna have to make sure I read chat out loud for the recordings. Okay, so this should do it. Let's just run it to make sure, because I be lying sometimes and messing things up. Great. Cool. We've got about 5 minutes still, so maybe we'll go over one more solution very quickly. But any questions about what I would generally say is like the optimal solution for this one here? Ooh, any ideas about does anybody want to take a stab at what the time complexity for this would be? Or does maybe somebody does have questions? I don't know. 3 people are typing. Does somebody else want to? Yes, it is O of N. Congratulations if you were typing O of N. Sorry, they beat you to it. Maybe you should be faster next time. It is O of N, and the reason for this is that we need to obviously still look at each element once. We could have just brute force this with a big loop. Yes, that is correct. And like we talked, I'm not sure, you may have gotten here afterwards, but when we talked about let me slow down. When we talked about the naive solution, we realized that was O of N squared, right? So as the data grows, it gets much, much slower. If we can make it O of N linear time, that's much preferred for us. And then I guess for context, because we didn't really directly address this, that tends to be what your interviewer is looking for in a software engineering interview. Is the naive solution tends to be somewhat easy to code. They're looking for you to make optimizations, to say, here's something that I think we could improve, here's how we can make this run more efficiently or faster or use less space or whatever it may be. So totally correct, that's exactly what we're doing. And that is, wow, that's a really loud helicopter. Wow, okay. Sweet. Yes, that is what we're doing. We're making it run faster effectively. And this one's actually quite nice because there's really not a lot of extra overhead to make it run faster. We have to do a little bit of extra work to check if we've seen the value. We do a little bit of extra work to store the value. Oh, damn, that bad, huh? Okay. Well, I'm back, hopefully now. But overall, we do relatively little work to improve the time complexity here. We do actually, so this is not something that gets talked about super often, but we do pretty dramatically affect the space complexity here because for every number, potentially we have to store it an extra time, right? But that tends to not really be as much of a worry. Will you code in C++ later? Maybe I will as a treat, but most of the time we'll be coding in Python purely because the goal is to teach you guys or refresh you guys on like the algorithm part. And generally speaking, like there's less in the way of the pure algorithm here when we're coding in Python. So maybe I'll think about it. Because I mean, I can code in C++, but I just will tend to do Python. Yeah. Oh, another comment. What do you have to say? Well, I'll let you keep typing. Do I have anything else I want to say here? Okay, so data structures we've covered so far. If you just tuned in, I think someone just tuned in, you missed the whole thing. I'm so sorry, but we will be posting recordings now. The first couple recordings were really choppy and like difficult to like listen to and watch. So I think they've smoothed out. So this will be here for you later. Face reveal when the server hits 500 people. No, I don't know. I mean, most of you guys have seen me. I presented live in front of your classes. So, like, there's no face reveal. You know what I look like. So, yeah. Man, y'all be typing. Yeah, you saw me in 3. Okay, good to know. Good to know. Why would we use a dictionary as a second array? Wouldn't have been just as fast to use an array. Well, here's the problem is that we're searching, right? And, well, just quick refresher of the data structure we've talked about so far. For an array or for a list, if we're checking to see if an element is in the list, we potentially have to look through all of the elements, right? Like, I know, like, this is, like, we can read this very quickly, but imagine if we needed to know, hey, have I seen 5 before, for example? Oh, wait, let me make sure I understand your question. Why would you use a dictionary with index value as a second array? Wouldn't it have been faster just to use an array? Well, yeah, I mean, I guess that does answer your question then. If we just stored the values, well, okay, actually, I should clarify for the problem. What we're returning at the end is the indexes. So if we just store the values, not super helpful to us, right? The other thing being, if we want to look through all the values, we need to store them in some way to say, I've seen this before. And then when we're done, we need to be able to say, okay, I've seen it before, and here's where it was, right? So if we use an array for either of these things, either it gets really slow to see if we've seen it before, at linear time, which is O(n squared again, overall, or we have no way of finding the number again. I guess what you could do, which just this actually doesn't affect the time complexity, is you could just use a hash set. Yeah, it is all about the indexes, but you could just use a hash set to store the values, and then you could just, once you know that you've seen it before, you could just look for it, which actually would still just be O of n one time, right? So it actually doesn't affect the time complexity. It's kind of funny. So let's just rework it, because why not? Let's say we just record what we've seen so far. Then we could say, if this is in the scene, ooh, and I think there's an index function for, oh wait, I don't remember how it works. Let's look this up real quick. Get index of element in list Python. So this is something I should know off the top of my head, but I don't. Okay, list.index. Okay, so you can just use the list. So we can say nums.index complement and then index here. And otherwise we say scene.add value. This should work as well. You guys are crazy. RTL monster dailies. I'm dead. Don't look at my personal information. So this actually works in an equal level of time complexity to our previous solution, and this is because we only ever have to look through the array once when we find the answer, right? So the problem earlier was for every single number we went, let's look through the array and see if we've seen the complement. Let's look through the array every single time, right? So n times n. In this case, actually, the outer loop is O of n. And then this is also O of n. So this actually doesn't affect the time complexity. And if for whatever reason we were strapped for space, this actually would work just fine. So it's trade-offs, right? And often with a problem like this, there's multiple solutions and the solutions have different strengths and weaknesses. This is totally something you could do in an interview to say, hey, if we you know, if we're trying to prioritize using less space, here's another way we could do it. It runs maybe a little bit slower, but overall, it's on the same scale of speed, right? So here's another approach we can take, which is great. I love that. I'm not going to have us go too long here because I just want to be respectful of you guys' time. But I think somebody else posted also a sort version of this where you sort it first and you can use 2 pointers from the ends to find the solution. So maybe take a look at that one. That could be fun. But let me think. I think that's all I got for you. Another helicopter. Oh my gosh. It's crazy. Oh, okay. I'm ending the stream. Love you guys. See you tomorrow for our last problem for the week.